Welcome back, Chem 107 students. We are now on our second video for Chapter 10. So we stopped on this slide. It was showing a nuclear explosion, and the brownish color is due to nitrogen dioxide gas, NO2. That's one of our main pollutant gases, and it also causes acid rain. So we talked about it a lot in Chapter 6. So in case you remember, NO2 from Chapter 6 is the brown color in a nuclear explosion's mushroom cloud. Well, moving on, now we're going to talk about fission power plants in this video. So a nuclear power plant is a power station in which the heat source is not burning coal, but it's the nuclear reaction in the reactor. Just like with coal plants, heat is used to generate steam that turns a turbine connected to a generator in a magnetic field that produces electricity. So again, it's all about boiling water, just like the coal power plant. So we need to create enough heat to boil water to turn into steam to float through the pipes that turn the turbines, which generates electricity. But instead of burning coal, we're just going to let the uranium fission occur, which generates a lot of heat. As of 2014, the International Atomic Energy Agency reports there are about 450 nuclear power reactors in operation in 31 different countries. 103 of those nuclear power reactors are in the United States and provide about 20% of our electricity. The uranium, or fissionable material, is not present in critical mass. Thus, it cannot explode like a nuclear bomb. Again, how stupid would it be to have critical mass in a power plant? Stupid, 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 so we don't. So again, a nuclear power plant cannot explode like a nuclear bomb. We don't have critical mass. The public is largely unaware of this fact, which creates fear and misunderstanding of nuclear power plants. Remember, uranium-235 is the fissionable uranium isotope, and it only needs to be at 3% to be useful in a power plant, compared to 85% in a fission bomb. Thus, the uranium at a power plant cannot be used to make a bomb in its current state. It would have to be concentrated with one of those gas centrifuges. So another mistake is people think you can steal the uranium from a nuclear power plant and make it into a bomb. That's not true. The power plant uranium is 3%. You need 85% to have a bomb. So your typical terrorist cannot go and steal uranium from a power plant and make a nuclear bomb out of it. So that's just another misconception. So some of the pros of nuclear power. 1 gram. That's a tiny amount, about the size of a piece of gum. A gram of uranium-235 has the same amount of energy as 12 million grams of gasoline. Nuclear power plants do not release greenhouse gases, which cause climate change. Yay, that's great! Due to less fuel being needed at the plant, the transportation cost of transporting the uranium is much, much less than that of coal. So at a coal power plant, the trucks and trains are coming on a daily basis bringing the coal. A nuclear power plant, you just need to fill it up about once a year. So all of those trucks and trains that are burning gasoline or burning coal and have tires and rubber, and the trucks are on the highways to transport the coal, you don't have that for a nuclear power plant. So that's a lot less pollution being created. Nuclear power plants do not emit NOx or SOx, so no acid rain, no pollution. They don't have mercury residues in the ash either, unlike coal ash. Also, there's less miners dying and getting black lung because we don't have to use as much of it. So those are all good things about a nuclear power plant. So what's the downside? Well, there's always the very small chance we could have a meltdown. That is when the reactor gets out of control and it creates so much heat that the factory melts. Now remember, it can explode. Cannot explode like a nuclear bomb. What we can have is we can have it melt, and then we can have chemical explosions, but not nuclear explosions. So that's no good though. We don't want our factories melting down because that releases some radioactivity in the area. The other problem is, where do we store the leftover fuel, which is still radioactive? So even though we use the uranium-235 in the nuclear reactor, at some point it's not generating enough heat anymore, but it's still a little bit radioactive. So we can't just put it in our trash, we can't put it in a landfill, we can't put it near people. So what do we do with it? So currently the exhausted fuel rods are stored temporarily in underwater ponds next to the vaults. Then it's stored in a concrete cask next to the power plant, and there's a picture. So inside that big concrete cask, there's an iron container with the spent uranium inside of it. And you can see a person standing next to it right there to see how big that cask is. And it's just sitting out in the open next to the power plant. So that's not the greatest thing. So what do we do with the waste? That's a problem. That's the con. That's the biggest con of nuclear power. So what do we do with the nuclear waste? The biggest problem with nuclear power is that waste. The waste contains leftover uranium and it contains plutonium that could be used as a weapon if it was concentrated. The spent nuclear fuel is the fuel rods after being used in the reactor. Now, mostly what's left over is 238, which isn't fissionable, but we do have some leftover 235, which will fission to plutonium-239. At each U.S. reactor, about 33% of the fuel rods are replaced per year. They are transferred to pools of water for a year, then dried and put in these concrete casks that you just saw a picture of. Most waste is stored on site in these concrete casks, and they're supposed to be temporary storage. So the United States doesn't reprocess the waste the way France, Germany, and Japan does. So again, what do we do with our waste? Well, it'd be nice if we would reprocess it like countries in Europe and Japan do, but we don't. I don't know. Here's a map showing the United States and where the reactors are. You can see by far most of them are in the eastern half of the United States. We only have 3 in Arizona out at the Palo Verde station, which is west of Phoenix, and there's 4 in California. But this does produce about 20% of our electricity needs. Did you know we have 103 nuclear reactors? I bet you didn't know that, did you? Yeah. So worldwide nuclear power plants. The first one was in the former Soviet Union in 1954. Right now, there's 450 nuclear power plants in 31 countries as of 2014. They've been building more, so we may have more now. 30 more under construction in China, Russia, India, and South Korea. They're all building. However, Germany and Switzerland are phasing out their nuclear power plants. In France, it's their main energy source. Overall, in the world, it's about 15% of the whole world's electricity. By the way, for comparison, coal is about 40% and natural gas is about 20% of the world's electricity. Here's a map showing the whole world. We can see besides the United States, the next biggest area for nuclear power plants is Europe and Japan and Russia. India is increasing theirs right now, and there's hardly any in South America or Africa and none in Australia. So India is increasing their nuclear power plants. They had 17 in 2009, but they were planning to build 36 more. China had about 11 reactors in 2009 with 17 under construction and plans for, get this, 110 more. So they're wanting to go nuclear, not so much coal, because of the greenhouse gases. How do nuclear power plants work? Again, we need the 235 uranium, which will fission by a controlled chain reaction. Not letting it go and letting it explode. We don't have critical mass. It's going to be controlled. Now, first of all, the 235 uranium is enriched from the 0.72% where it's found in nature to about 3%, and we put it in uranium fuel rods. The fuel rods are about the size of a pencil. Okay, they're not very thick. Okay, a fuel rod could look something like this. about similar to the diameter of a pencil. We use boron control rods to go between the uranium rods to slow the reaction down. So for example, if these are the uranium rods in a reactor, boron rods come in between them and it slows or shuts the reaction down. Then we pull them up to open up the reaction to go. If we need to slow it down, we lower the boron rods a little bit. So the boron control rods slow the reaction down. And we produce enough heat that water is boiled by this heat of the fission. It's turned into steam. The steam then floats down pipes and turns the turbines that rotate within a magnetic field, which generates electricity. All of that is just like a carbon power plant with coal, right? Coal burning power plant. The whole point is to boil water. So here's a picture of the power plant. So on the far side, the left side, you can see the orange area. That's where the nuclear reactor vessel is. And we have the uranium rods and the control rods going up and down, controlling that reaction there. That's where the heat is generated. That heat then goes through the orange pipe and back, just continually flows, that first cycle. Then the blue is where we have the water. So where the red pipe goes into the blue is where the water heats up and turns to steam. Steam floats up and over to the turbine, turns the turbine, which turns the generator, which creates electricity. Then the turbine steam flows down and goes to the condenser, where it gets cold and returns into water. Okay, so it condenses. And then we have water that goes back over to the reactor vessel, where it heats up again. Now finally, we need to have a third flow of water in the condenser. It's just cold water coming in to cool down the water from the turbine, and then it flows back out. This is often just water from a river, a lake, a stream. So usually it's water from there. Well, Palo Verde's west of Phoenix. There's no river there. Where do you think the Palo Verde nuclear power plant gets its water? I bet you would never have guessed this. It's from toilet flushing. That's right. When we flush our toilets, we send the cold water out to Palo Verde, where it circles through and cools down that steam to turn back into water to go back through. Yep, pretty crazy, huh? Here's just another picture of the power plant. You can pause here if you want to. Again, A is a big concrete containment structure at the power plant, and those are designed to resist being hit by an airplane. Okay, again, they're double-hulled to resist being hit by an airplane. So you can't crash an airplane into a nuclear power plant. And remember, it can explode like a bomb anyway, but a lot of people don't know that. B is the control rods of boron that go down. K is the fuel rods of uranium. C is the reactor itself. F is the pump that pushes the water to go through that gets heated up. D is where we have the steam generator. That second flow of water gets heated up, pumped through E, the steam line, down to H, the turbine, where it turns G, the generator, which creates L, the electricity at the transformer. I is where the cooling water comes in and cools and condenses the turbine water back to F, where it goes to another pump to go back over to D inside the steam generator. F is another pump to get rid of the cool water, and it can go, like at Palo Verde, we have J, cooling towers. Now the cooling towers put off steam, extra steam, but it's not greenhouse gases, it's not pollution, it's not smog or smoke, it's just steam. So when you drive to LA, if you look to the left about an hour out of Phoenix, you will see 3 big, large cooling towers with steam coming out. It's not pollution, it's just water vapor. That's it, water vapor. So just looking more closely at parts of the reactor, blue is the boron control rods, red are the fuel rods, and you can move the blue rods up and down to control the reaction. So again, once we pass through the reaction, we turn hot, which is red, and it flows out and goes through the water container where that water boils and turns into steam. So the steam then is that gray cloud. We make that water boil to steam, and then it goes through the pipe to the turbine. And then the turbine turns, generates electricity. The steam cools back down, is pumped to the steam generator. The condenser water is sent to the cooling tower, and that's what you see, the steam coming out of the cooling tower if you drive by a nuclear power plant. So, production of plutonium in nuclear reactors. One of the products of the uranium fission is 239 plutonium. 239 plutonium can also fission by absorbing a neutron and can produce about a third of the energy. Plutonium-39 is relatively stable. It has a half-life of 24,000 years. So it's also used in nuclear weapons. Several countries reprocess the spent fuel and use that plutonium to put in their nuclear weapons. Or you can put it in a different kind of nuclear power plant. So that's very interesting. You can use the leftover fuel of one reactor to power up a second reactor instead of mining for that fuel. That's what France does. Pretty smart. So these breeder reactors is what they're called, a liquid metal breeder reactor. They use neutrons from the 235 uranium fission on 238 uranium to produce the 239 plutonium. You don't have to remember all that. But in 10 to 20 years, you've made enough plutonium that'll power a whole nother reactor. Now, these reactors don't use just water as a coolant. They use liquid sodium as a coolant, which has to be under pressure. Uranium also has to be 15 to 30% enriched, not the 3%, to generate power with the fast neutrons while breeding the plutonium. So that's getting closer to weapons grade at 85%. So, a little bit more dangerous perhaps. Still, it's not weapons level, and it's still not in critical mass. There was a huge nuclear reactor in France called the Super Phoenix, and it operated for 20 years using this breeder reactor technology. It extends the usefulness of uranium by 60 times, so you don't have to go mine more uranium, which of course is devastating to the environment when we mine uranium or mine anything. So it's nice that we can reprocess this fuel and use it instead of having to dig it up and ruin the environment. So because of all these positives, there's renewed interest in the breeder reactors right now. There's also another kind of reactor besides the one we have in the United States. Canada uses one called a deuterium uranium reactor. It's called CANDU for Canada. It uses heavy water, D2O, as a coolant instead of regular water. That just means the hydrogen atoms have an extra neutron. The uranium ore needs no enrichment at all. It can be used straight out of the ground at the 0.72%. That's good. So again, Canada uses this technology. We call them CANDU reactors. 6 other countries have followed suit and used them as well. Overall, CANDU reactors use 30 to 40% less mined uranium than a typical light water reactor, which is what we have in the United States, per unit of electricity produced. This is a major advantage. It not only requires less fuel, but the fuel does not have to be enriched, so it's much less expensive. So again, you can just take uranium straight out of the ground and don't have to enrich it at all. So you should remember, other types of nuclear reactors besides what we have in the United States are breeder reactors and CANDU reactors. Those have significant advantages over what the United States uses, which is a light water reactor. So the future of nuclear power. Countries of the world are each planning their own course of nuclear plant development or decline. Nuclear power is now competitive with natural gas. It is non-polluting. It does not contribute to global warming. Obtaining the fuel only takes 5% of the energy output. The newer designs are much better than what we use in the United States, meaning the CANDU and breeder reactors are better than the light water reactors. The waste disposal, though, is still an issue. We need to solve that, and it's being studied. And we're going to stop this second video here. We're going to talk about some nuclear accidents next. So goodbye, GCC. Have a great day.